Alright, section 2.3. We're just going to get right into what an acid is and how certain acids work and pH and all that kind of stuff. We're going to begin with what an acid is. So an acid is a substance that increases the concentration of H plus in a solution. So an acid increases concentrations of H plus. It's some kind of chemical that when you add it will increase the H plus concentration. Now, we're almost always going to be talking about this in the context of water. So it's almost always a substance that when we add it to water increases the H plus concentration of that water. And to say that something is therefore acidic is to say that it's already got an acid in it, and therefore it's already got its H plus concentration increased. So something is acidic, it has a very high H plus concentration. Acidity is the H-iness. That's all it is. It's not the plusiness. It's not about how many positive ions it's got. It's about how many H plus ions it's got. An important definitional thing here is that an H plus ion is a hydrogen atom without any electron, because a hydrogen atom is just a proton. H plus without any electron going around it is just a proton. So it's the proton concentration in a substance as well. To say H plus is synonymous with saying a proton. So that means that if we say that something increases concentration of H plus, it means it is a proton donor. It's the same thing. So that's one important definitional thing. The next thing is if we're talking about water, there's an equation that matters. H plus H2O goes to H3O. So in a liquid environment, H3O plus, the H pluses don't go around freely, they join on to water molecules and form H3O. So there's a fair bit of information there. The important thing is that an acid is something that increases the H plus concentration. Acidity means that it's got a lot of H pluses, and that the H plus proton doesn't just move around freely. It'll often be joined, well, it will be joined on to the H2O molecule. Now, sometimes we say that the H plus, we refer to it as just an H plus. Sometimes we refer to it as an H3O. It depends on the context as an H3O plus. But in an aqueous solution, the H plus will, as a practical matter, be joined to the H2O. It's just that we may or may not express that in the equations, depending on whether it makes things clearer or not. So that is acidity. Move straight on to another important definition, and that's pH. And I think the best way of approaching this is to first of all talk about an important equation that goes on in all water, in any glass of water this is going on. And that's this. It's an equilibrium reaction. It's got a forward and a reverse reaction. And in fact it's heavily skewed to one side, to this side. But it's H2O goes to H plus OH minus. That's the ionization of water equation. And what it means is that every once in a while, one of these H2O molecules, so any H2O molecule, any water molecule in a glass of water, is prone every once in a while, not very often, as it turns out, because the equilibrium point is way to the left, but it still happens. It will split into an H plus and an OH minus. So the water molecule will essentially split, and then we have an H plus concentration in an ordinary glass of water. So pure, completely pure glass of water, if it started with all H2O, you will get some H plus and some OH minus molecules floating around. No question. Now, the thing is though that because this reaction is so far to the left, we don't get very much of this going on. In fact, we only get 1 times 10 to the negative 7 moles per litre of H plus, and of course it's the same number of OH, it's just come from H2O. So that's the concentration we get. Now that in non power of 10 terms, that's 0.0000001 moles per litre. That's not very much. So it's a reaction that's a long way to the left. But what it means is that even in an ordinary glass of water, an ordinary glass of water, in any body of water that hasn't had any acid or any base added to it, it's got H plus molecules in it, it's got OH molecules in it, and they're at a certain level. And it's for this reason. So we're just talking here, by the way, about H plus concentration. So that another way of talking about the H plus concentration is to use this symbol, the big square brackets, and OH concentration, similarly OH minus concentration, it's the square brackets. So we're just talking about that here, and we're saying it's this many moles per litre, not very many. We haven't actually talked about pH yet. But it's the fact that even without adding any acid, that we get a certain number of these molecules. That is why we say that a neutral pH equals 7. So if we don't add any acid or base, we get a neutral pH of 7. So the reason we say a neutral pH is 7 is because you'll remember there's a concentration of 0.0 blah da 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 0.00000 6 zeros and then 1 moles per litre of H plus in substance. So there's that much of it in there. There's not a zero amount of pH, and we'll get to a zero amount of H plus concentration. Now to get the pH from that, basically the pH is just a way of dealing with the fact that there's a lot of zeros in any number of moles per litre, and that this number changes incredibly rapidly as you add acidic substances. So instead of counting the exact number of moles per litre, we use pH, which is a logarithmic scale. I'm not going to go into the full definition of a logarithmic scale, except to say that if something is pH, I'll just give examples because I think it's easier than defining it. If something is pH 6, that means it has 10 times the concentration of something that's pH 7. And if something's pH 5, it's got 10 times, it's 10 times again, concentration of 6, which means that something that's pH 5 actually has 100 times the concentration of something with pH 7, and it keeps going. pH 4 has 10 times again 5, which means it's got 100 times the pH, the concentration, the H plus concentration rather, of something that's pH 6, and 1,000 times the H plus concentration of something that's pH 7. Now, how that looks in terms of moles per litre, once again, might as well just write it out. So pH 7 means it's got 0.1, 2, 3, 4, 5, 6, and the 7th digit is a 1 moles per litre. That's the best way of writing it out. I just count along, and then the 7th digit is a 1 because it's pH 7. something's pH 6, it's got 10 times as much. So it's not that difficult. It's just on the 6th character. It's pH 6, pH 5. Once again, it's got 10 times as much again. 4, 0.1234. Okay, in terms of how to calculate the pH, the equation is that the pH equals negative log 10 of the H plus concentration, which is exactly how I just explained it, the number of zeros. Basically what this log 10 function in your calculator does is it counts the zeros either before or after a number, and it's a count of that. So you say log 10 of 100, that's it's basically going to say, well, that's 2. And that's because it's 10 to the power of 2 equals 100. Now when you go the other way and you say, well, what's log 10 of 0.01? Well, it says, oh, well, there's 2 zeros, it's 2 decimal places there, so that's negative 2. So it takes whatever's in here and it says, well, what kind of power of 10 are we dealing with? And of course, if we take the negative of that, we're going to reverse the sign. So if something is very, very small, it gets a bigger number the smaller it is. And that is exactly how pH works. So because this has 7 zeros in the case of neutral water, we get, well, sorry, 6 zeros, 7 decimal places, and it's got a negative log 10. We get the log 10 of it is negative 7, and the pH of it, so this is moles per liter, concentration, pH equals 7. And the reverse of that is to find the pH concentration, is to find the concentration from the pH. And the way we do that is we say the concentration of H plus ions is equal to 10 to the power to the negative power of pH. And that's just the reverse of this equation. Something you'll deal with in certain maths courses. Log 10 converts around to 10 to the power of, if you want to get the thing that it operates on, if you want to find that. So that's how the logarithmic scale works. That's how you calculate it. pH equals negative log 10 of the concentration, and the concentration equals 10 to the power of negative pH moles per liter. Alright, so now we'll talk about a way that pH can change, and this is going to be a pretty common way that pH can change if we add an acid to a substance. So you'll remember that to begin with, we're sitting there at a pH of 7, which means that there's only a very, very small number of H plus ions. And if we want to change the pH, or whether we want to or not, if something happens that changes the pH, that's gonna happen by manipulating this number in one of two ways. The first way is that a substance can add H plus to the solution. So we could have a bunch of water that's happily there with only 1 times 10 to the negative 7 molecules of H plus in it. But then we could add, let's say, 0.1 moles of HCl, and HCl, hydrogen chloride, hydrochloric acid, ionizes completely to H plus plus Cl minus. Now you'll note that we've added a whole lot of negative ions to the liquid. That does not affect pH, has no effect on pH whatsoever. But if we add H's, we add H plus ions, that does affect pH, it does affect the acidity of the substance. We've made it more more acidic, we've made it more H plusy, and that's going to change the pH. How is it going to change the pH? Well, now there's a new number of H plus ions in the substance. Now, because we know that every single mole of HCl is ionizing, we know that for every mole, these 0.1 moles of HCl, we got 1 mole of H plus. We can calculate a new pH based on that. We now know, let's say that we added it to just 1 liter of water. Need to know the amount of water that we added this moles. We now know there's 1.1 moles per liter of H plus. In the substance. So H plus concentration 0.1. We do the equation. That means the pH, it's always a little p followed by capital H, equals negative log 10 of the H plus concentration. I can write that out, 0.1. Now, log 10 of 0.1 is negative 1, so it equals negative 1, which equals 1. So the pH of this substance is 1. Okay, so if you've been watching closely, you'd be wondering now, well, why did we only count the 0.1 moles per liter of HCl, and that therefore it's the same amount of H plus, or when I put it a different way, H3O plus. Why did we only count that and not the original ionized H2O? Remember, this equation is going on at the same time. And there's a very simple reason that we didn't count that H plus from this, and that is that it's so small that it doesn't matter. And this comes up, or rather doesn't come up in acids a lot, because if the pH of this equation is 7, that means it's 0.00000001 mole per liter. And when you add that to something that's pH 1, which is 0.1, that just means that it's 0.000001 moles per liter. And that's basically the same number. I think mathematically this number is not very different to 0.1 because we're working on such a completely different scale. What happens is that when we calculate the pH of this, it's the exact same number as the pH of this one. These two numbers are so similar, it doesn't show up on the pH scale. So that's why we ignore the ionized water. So that was an important point to make. Okay, the next thing to have a look at is ionization of the acid, and strong acids and weak acids. So we'll get to that now. Now, last example was a very good one of a strong acid. The HCl just had a one-way reaction that went to H plus Cl. Now, Cl minus. Now, when it's got a one-way reaction, what that means is that all of this is turning into these. So that means that the substance completely ionizes. Now, this is in contrast, of course, to the H2O reaction. I won't write it out, but you'll remember that it had symbols going both ways. It wasn't a complete ionization. This is a complete ionization reaction, and that makes the substance HCl a strong acid. By the way, that doesn't make H plus an acid. H plus is the thing that we're measuring when we're determining if something is acidic, but the actual acid is the thing that gives up the H plus increases the H plus concentration. So that's important to remember as well. But the HCl is a strong acid because it completely ionizes, completely turns into H plus. And to understand why that's a thing with a name, we should look at a counterexample, something that doesn't do this, and there isn't a better example than acetic acid. So acetic acid is CH3COOH, and it's a very common weak acid, and it'll come up a lot in the course. And when it ionizes, it goes to H plus plus CH3COO minus. You can see that there's some broad similarities here between the two equations. We've got a substance that undergoes a reaction, gives up H plus, so that makes it acidic. So this is acetic acid. Also ethanoic acid, same thing. And it splits out to H plus plus CH3COO minus. But the big difference is this here. It's got a reverse reaction as well as a forward reaction, which means that at any one moment there's going to be some, remembering our equilibrium, there's going to be some completely intact acetic acid molecules, and some of them will be ionized. Now, the proportion of CH3COOH molecules that haven't ionized, this proportion are not going to be contributing H plus to the substance because they've still got the H plus attached to them. So what that means is that this acid is not going to contribute all of the H pluses. It's not going to contribute as many H plus ions as it has molecules. Only a proportion of them are going to be contributed, and that means that it's a weak acid. It undergoes incomplete ionization. So that is a typical weak acid. It comes up a lot, and anything with a carbon structure, a carbon chain, a carbon spine with one of these COOH molecules is going to be a weak acid. So you'll get used to seeing the COOH group and knowing that that COOH group functionally, it's a functional group of course, goes to COO minus plus H plus. Alright, I'll just make a quick point here about OH because it's important. Just as there are strong acids, there are also strong bases. And there are weak acids and there are weak bases. So let's talk now about how that's going to work, because we already know if something's an acid, it adds H plus. So what's a base do? What's the opposite? And it is the opposite of adding H plus, because a strong base will reduce the H plus concentration and it will therefore increase the pH, whereas acids of course reduce the pH. How does that work? Well, it works through the mechanism of donating an OH minus to the substance. So a good example is potassium hydroxide. That goes to potassium plus OH minus. Now, because in water we have an equilibrium reaction where the H plus interacts OH minus, if we contribute something that increases the OH concentration, and we know from Le Chatelier's principle that what that's going to do is that's going to force the equilibrium to the other side. well, the equilibrium's going to kind of down change, but things are going to shift to the left. Because we've disturbed the system, we've added OH, that means more OHs are going to run to H pluses, so we're going to get less H plus and more H2O, although we won't really notice if we get a small increase in the number of water molecules in a big, big substance, big container of water molecules. Not going to notice any real change there. But we are going to reduce the H plus concentration because there's more OHs bouncing around, interacting with them, and that's how we can get an H plus concentration that's even lower than 0.000001, which is neutral, that's pH 7. We can actually get it much lower, right down to 13 zeros and then a 1. So move that all the way, another 7. And that's actually how pH and pOH work. So that's how the OH concentration affects the H plus concentration. And the way it works in practice is that the pH concentration equals 14 minus the pOH concentration, and pOH concentration equals 14 minus the pH concentration, or we could say that pOH plus pH equals 14, and that will always hold true. And you can treat pOH exactly the same as pH in terms of the calculation and the equations. So what that means is that if anything donates OH minus ions to a substance, what that really means is that it goes around scrubbing up H plus ions. So if we increase OH minus, we're going to decrease H plus ions, and it's acting as a base. So it's the opposite of an acid, and it's going to have that effect on the substance. And yeah, we have strong bases as well as weak bases, just like we have strong acids and weak acids.